representation of complex numbers. Now, didn't we already learn that? Didn't we learn a plus bi is a representation of a complex number? Yes, it is one of the representation of complex numbers. So we'll learn two more apart from that. Representation of complex numbers. Okay. So the first form of representation of complex number is what we call as the point form representation. Point form representation. Okay, so when you write a complex number as a plus bi or a plus ib, I mean, doesn't matter whether you write I first or I later on. This is actually called a point form representation. Now, why it is called point form representation? It is because you can represent such a complex number just like a point on a plane which we formulate by using a real z-axis and an imaginary z-axis. Not to be used x and y. Please don't use x-axis and y-axis here. It's a different kind of a plane which we name as the Argand plane. Which we name as the Argand plane. It is also called as the complex plane. It is also called as the Gaussian plane. Gaussian plane. Okay. All three are basically the name of the same plane. So in this plane, we normally represent any complex number just like a point. So this z could be represented just like a point a comma b. Okay. Don't call a as the x coordinate, b as the y coordinate of the point. I know it is very similar to the coordinate geometry, and hence coordinate geometry fundamentals can be used on complex numbers. Remember in the beginning of the chapter, what did I tell you? This is the chapter which has got many faces to it. Okay, one of them is your coordinate geometry representation, or your fundamentals of coordinate geometry can be used. So if you represent a complex number just like a point on the Argand plane, so it will look like this, and that's why it is called a point form representation. Later on, we will learn when we are learning applications of complex numbers in geometry that how section formula, etc. can also be used on it. Distance formula, section formula, absolutely Anurag, they will all work on it. Okay. Any questions here? Any questions over here? Okay. Now, two important things that we need to understand over here is the concept of modulus and the concept of argument, also called amplitude. Okay. Now, what's a modulus of a complex number? Modulus of a complex number, first of all, is represented by the symbol z, and it basically represents what is the distance of the a comma b point, which is basically the point form representation of the complex number, from the origin. Okay. Now we are going to soon use this concept very, you can say frequently and on a very large scale. So please understand this concept. It's very important. More importantly, what does it represent actually? So if you see, this point is called the origin, and the distance of this complex number from the origin, this will be called as mod z. Okay. So mod z is what? It basically, or modulus of z is what? It basically represents the distance of that point a comma b from the origin. Correct. So how would you find the distance of any point from the origin? So you'll say it is simply under root of a minus 0 square b minus 0 square, which is under root of a square plus b square. Am I right? Correct. This is how we know the formula. So this is how mod z or modulus of z is defined. Remember, it is always a positive quantity. It is always a positive quantity because it represents distance. How will it be used? Where will it be used? We'll understand in some time. But just understand as of now, what is modulus? Modulus of a complex number is nothing but the distance between the complex number represented like a point on the argand plane from the origin. It is defined like that, Anurag. You cannot challenge a definition. It is defined like that. You are confusing with the mod of the real numbers, where it gives you a absolute value. That mod is different. This mod is different. You can compare this with the magnitude of a vector. Vector you have done, right? How do you find the length of a vector? How do you write? Let's say I take a vector P, which is, let's say, AI plus BJ. How do you define the length of a vector? Under root of A square plus B square. Am I right? Correct? How? Why it is written like this? Why it is written like this? Now, can you answer the question? Why mod is, you're asking, no, how is the mod the distance from the origin? So how is mod of P under root of A square plus B square? This is how it is defined, because this you are finding the distance. It is defined as the distance. Are you getting my point? Okay. See, when something is defined, you cannot challenge it. Mod of a complex number is defined as the distance of the complex number from the origin. Period. You cannot say how. Then you can say how mod of -3 is 5. Who has defined it like this? Arey, that's what I'm saying, no, Aditya. It signifies the distance. It signifies the distance of the point from the origin. That is how it has been defined. Now, Anurag is asking how it is defined like this. There's no answer to that. How do you say mod of P is this? Of course, you'll say length, we have to use Pythagoras theorem and get the formula. Ultimately, it comes down to finding the length. Same way, finding the length of the line segment connecting origin to A comma B is this. How can I explain it further? I can say Pythagoras theorem max to max. It is very different. Modulus in a real number gives you absolute value of the quantity. Modulus in a complex number, or for that matter, vectors, gives you the length of the line segment connecting origin to that point. That is how it is different. Achha, I understand now you are getting confused by the use of the word modulus. Modulus doesn't mean always the absolute value unless until you are talking about only in real sense. Okay, we use modulus in vectors. We use modulus in complex numbers. Correct. Degree word. If I say degree, does it always mean a temperature? No, if you're talking about in temperature, degree means one of the units of measurement, right? But degree in polynomials means something else, right? So same word has different meanings. Yes, exactly, Madhav. Didn't I say in the earlier, I think you joined a little late. Complex numbers have characteristics of vectors. It is actually a position vector. It is actually a position vector. Yes. When you say A plus BI, A into 1, B into I. 1 is acting like your I vector along the Z axis, or you can say a real Z axis. And I is acting like your J along the imaginary axis. So if you want to reach a point from A to B, we basically go A times 1 unit along the real axis and B times I along the let me not write I cap, it is just I. I cap will become a vector thing. So it is synonymous to that, right? So when you're finding modulus of a complex number, it is synonymous or it is analogous to finding the length of a vector which is written as a plus, or you can say a1 plus bi. Is that fine? Yes, absolutely. So if you take a minus 5 comma 0, which actually is represented like minus 5 as a complex number, here mod z will basically act in the same way as the mod of the real numbers. So you can say mod in that case is a very special case of it. So I'm just, you can say, extending it to cover up a two-dimensional number. Now got the point? Now all the queries in your mind is addressed. So how mod of real number is similar yet different from a mod of a complex number. Similarity will come when your complex number is a purely real complex number. Difference will come when it has got some imaginary character to it, right? So in reality, when you are writing any number, let's say I write a 5, you are actually writing it as 5 into 1 plus 0 into I. And ultimately, when you do this operation, which I have now discussed with you, you end up getting 5 only. So Pranav has very beautifully summarized that if at all you have a purely real number, it will, modulus will act in the same way as the modulus that you had learned while you were studying real numbers. Make sense now, Aditya, Anurag, Madhav, all your doubts addressed? Okay. Geometrically speaking, it represents the distance from the origin. Okay. The next thing that we are going to discuss is the amplitude slash argument. Okay. That is something which I'll take on the next page. So here I would like to take some examples before I move on. So if somebody says, hey, what's the modulus of 3 plus 4i? Your answer would be under root of 3 square plus 4 square, which is 5. Achha, one mistake which I would like to point out here, you may also end up doing the same mistake. Please do not do under root of 3 square plus 4i square. No, this is not what I'm trying to tell you here. It is just a square plus b square. It is not a square plus bi square. No. If you do this, it will be wrong. This is not your mod z. Please don't get this wrong notion in your mind. Okay. It is just 3 square. So even if somebody says what is the modulus of this, it is still going to be 3 square and minus 4 square, which is going to still give you a 5. Is this fine? Now, going to the concept of argument slash amplitude. Okay. Now, argument and amplitude has basically come from the concept of the polar form representation of a point. Remember when I was doing trigonometry with you, I told you that if you have a point A comma B, you can represent this point position in an alternative way also. And that way was representing how far is this point from the pole and what angle does this line make with the x-axis, right? Do you remember? You remember I said this distance was r and this angle is theta, right? So when you were learning the polar coordinates of a point in trigonometry, this is what we had discussed. Okay. So a comma b is the Cartesian form, and when you represent it by suggesting its distance from the pole, this is what we call as the pole, and hence the name of the coordinate system as polar. We normally mention its distance from the pole and this angle, right? Do you remember that? Now this r is what we learned just now is the modulus. Okay. And this theta is what you will call as the argument. Okay, also called as the amplitude. Now don't get confused with the amplitude that you have seen in your physics. Normally amplitude tells you what is the maximum displacement from the mean position, right? It is not that amplitude. However, the word amplitude has the same spelling as what you know in physics, but it basically represents the angle. Okay, mostly argument word is used. Amplitude word is very, very rare. I mean, if at all you see some JEE books, they will use some amplitude word, but mostly they will use the word argument. Now, there are two types of arguments that we are going to talk about. Your arguments can be either general argument, okay, or it could be a principal argument. Guys, please pay attention to this because this is very critical. And it is directly going to be one of your questions in your school paper. Now, there are two types of argument. One is the general argument and other is the principal argument. General argument is basically any angle which signifies this angle. Now, what is the meaning of any angle that signifies this angle? So any angle which signifies this terminal position. Remember when I did angles with you in trigonometry, I told you there is an initial position and there is a terminal position. Yes or no? Correct. So I'll take an example here. Let's say my complex number is 1 plus I. Let's say I take an example. Okay. So 1 plus I is like a point 1 comma 1 on the Argand plane, right? On the Argand plane. Acha, while drawing the Argand plane, please do not write X and Y here. It is not X and Y. If you do that mistake in your school exam, straight away teacher will cancel out. It is real axis and imaginary axis. Don't call it X and Y. Even though your fundamentals of Cartesian coordinate geometry is going to be applied, but you should maintain a distinction between complex plane and Cartesian plane. Yeah. Now, if I ask you, hey, what is the angle that this line makes with the real Z axis? So what is this theta? What is this theta? Now, several people can say several different angles. For example, Madhav can say pi by 4. Okay. Aditya can say 9 pi by 4. Correct. Anurag can say 17 pi by 4. Yes or no? Somebody can go the other way around also. Somebody can say, minus 7 pi by 4. Are you getting my point? So, for the same terminal position, this is your terminal position and this is your initial position. There could be so many angles or there could be so many co-terminal angles which can be used to signify it. So all these values that you have, they will be called as the general argument. That means everybody can state their own angle they want. I can take 7 turns and give you an angle. So I can say 14 pi plus pi by 4, 17 pi by 4, or let's say 57 pi by 4. Are you getting my point? So all these angles would be called as the general argument. So now, when you follow your own sweet angles, won't it create a confusion in the mind of a reader with respect to where is that complex number situated? Right? So if somebody says, hey, sir, there is a complex number whose modulus is √2 and argument is 57 pi by 4. I'll be thinking 57 pi by 4 means I'll figure out, okay, where it should lie. So it'll eat away my time. It will eat away the time of any person who is trying to infer from that angle where it is actually lying. So this is slightly time taking or confusing. Okay. So it has got a drawback that it is confusing because everybody can state his own sweet angle to state this theta. So what it was decided, let's have a unique angle, and they can be infinitely many. Correct? So it was decided that let's have a unique angle which lies between, I think it is slightly lagging, so I'll switch off my camera for some time. Yeah. So there should be a unique angle which should be lying between minus pi to pi to represent that angle. If that is the case, then anybody can figure out the position without much problem. So it will not be like a puzzle for him to solve, to get that particular complex numbers position, right? So it was decided by the consortium that if I choose this interval, you can signify any number or any complex number in this Argand plane by a unique argument. And that argument was called as the principal argument, right? Principal as in main, mukhya, right? Just like your principal of the school. Okay, so if somebody has to say the principal argument here, the principal argument for such a complex number would only be pi by 4. This will be your principal argument. There cannot be any other argument. Okay. Now, just an extra information which I would like to share with you, but this is not followed in your competitive level exam. Normally, any general argument is written by this acronym, small a r g with z. Any principal argument is written with the acronym capital A R G, which is Z. Okay. However, I have seen your JEE books, probably your NCRT books, if you're following any, they do not care about this. They use small a, capital A as per their whims and fancies. But this is what international books follow. So if you look at your IB books, I think some of you who have come from IB background, you'll come to know later on that they use these kind of distinction. But normally in your Indian books, they do not use this kind of distinction. In your Indian books, unless until stated, they always talk about principal argument. So use this unless until stated otherwise. Unless stated otherwise. So if the question says the argument of so and so complex number is so and so angle, of course you'll come to know that it's a principal argument or not, because your principal argument will always fall between minus pi to pi, minus pi excluded, pi included. Now why minus pi excluded, why pi included? Again, this is a convention that we follow, because let us say if I want to represent a complex number which is, let's say, located here, minus 2 comma 0. Let's say this is my complex number. So my complex number is minus 2. Correct. So what should be the angle? Should the angle be theta or should the angle be minus theta? Oh, sorry. Should the angle be pi or should the angle be minus pi? So it will create two answers, right? Right? Because pi will also lead to the same position. Minus pi will also lead to the same position. So to avoid this confusion, it was decided that we will only take the pi value, will not take the minus pi value. Is this fine? That's why minus pi was excluded from the interval so that nobody can state it. Got the point? All right. Having said so, I will officially define principal argument for you. Principal argument is defined as the shortest angle between the positive real z-axis and the line connecting, or the line segment connecting. Let me write it, line segment connecting the complex number z with the origin. A special care should be taken that if this angle is realized in an anti-clockwise fashion, it is to be taken as a positive angle. And if this angle is realized in a clockwise fashion, it is to be taken as a negative angle. Okay, I'll give you certain examples for it. Meanwhile, just note it down. We'll take up many questions. We'll talk about it, Anurag. I've just started this discussion on argument. So we'll take some examples. It will make it very clear. I'll take several examples. Let's say I want to find out. Let me first start with minus 1 plus I. Okay. If I want to find out the argument of this complex number, so what is the argument of this complex number? Okay, let's simultaneously also do modulus of the complex number. Modulus, you can all tell me easily, it's minus 1 square plus 1 square, which is actually root 2. Okay, so as you already know, modulus signifies how far is that complex number from the origin. So let's say if I represent this complex number, it will fall over here. Okay, and modulus basically signifies this distance. Okay, now I want to find out the principal argument of this complex number. So principal argument is, as you can see, shortest angle between the positive real z axis, and the line segment connecting z with the origin. So this is your z point. If you connect it to the origin, what is the shortest angle? Now, will the shortest angle be this way? You say no, sir, that is not the shortest angle, and moreover it will exceed our minus pi to pi interval. Okay, so your shortest angle has to be this angle. Now when you're realizing this angle, you are going in an anti-clockwise fashion. So anti-clockwise means your answer will be some positive quantity. So let me write a positive quantity, even though you don't have to write it while you are actually writing the answer, but just to make you understand, since this is our first example. Okay, so what is this angle? You will say, okay, this angle magnitude wise it is 45 degrees, so this is 135 degree. So 135 degree means 3 pi by 4. So this becomes your principal argument for this complex number. Make sense? Make sense? Now another question comes to me, sir, do we have to write it in radians? Degree mein nahi chalega kya? See, I would suggest you to write it in radians, because later on we will be using this in the Euler notation. Okay, and in Euler notation only radians will work, not degrees. Okay, so write it in radians only. I'm sure you are all comfortable with radians. Is this fine? Let me take few more examples. Let's take minus half minus I root 3 by 2. Okay, so if somebody says, hey, give me the argument of this complex number and give me the modulus of this complex number. Modulus is fine. Modulus, we can do it in one shot. I hope nobody has any problem with the modulus. Modulus is super easy. So this will give you under root of 1/4 plus 3/4, which is going to be 1. Okay. Now for the argument, we will have to position this on the argand plane. Okay. So if you position this on the argand plane, it will be here, right? Somewhere in the third quadrant, correct? So this is minus half minus root 3 by 2. Okay. Now, connect this to the origin. Connect this to the origin. Now, which is the shortest angle starting from the positive real z axis to reach this line? You'll say, of course, this route. And as you can see, you are taking a clockwise path. The shortest path is the clockwise path. So the answer will be some negative answer. Correct? Now, what is that magnitude part? Let us check it out. So if you complete a small reference triangle over here, just for your internal understanding, this is going to be half the length. This is going to be root 3 by 2 length. So this angle has to be 60 degrees if I'm not mistaken. 60 degrees. So this angle magnitude wise is 2 pi by 3. So the answer will be negative 2 pi by 3. Make sense? Make sense? Any questions? No doubt. Now the line segment that connects Z with O, the length of that is mod Z. That's what you can understand from there. Nothing more than that. Okay. Or you can say that the line connecting Z with 0 is basically a position vector. So if you just make a vector like this, it'll just make this complex number look like a position vector. Okay. So complex number position can be also be treated like a position vector. Okay, so if this is understandable, I'll have some questions for all of you. Let's take a small question. Find, or let me check if I have some questions with me on my question list. They all look to be the slightly difficult ones. Well, right now I'm not able to see any simple question for you to solve. So let me give few from my side. Find the modulus and principal argument for the following. Let me start with, let's say 10, minus 10, I, minus 3I. So a few basic ones. 0. 0 is also a complex number, yeah. Let's have root 2, negative root 6I. Let's have minus 1 minus I. Okay, I think more than this we need not do. Let me write it in yellow only. Okay, now let's do one by one. We'll solve it simultaneously. So first one, your answer should be two numbers. First should give you the modulus, and comma, the second number should give me the argument. So for example, for the first one, your answer should be modulus comma argument, and put the question number 1, so that I know you are on the right track. Oh, one second, Akash, just give me a second. Akash wants me to go to the previous slide. Yes, Akash, tell me. Let me know once you're done. Done, okay. Right, so first answer, 10, 0, absolutely correct. 10, 0, very good. Second answer, we have just now done this. Yes, 10 pi, very good. Okay, remember the shortest angle could be minus pi also, but as per our interval convention that we follow for principal argument, minus pi is not to be included, so it can only be pi. It can only be pi. Never write a minus pi even by mistake. Okay, third one, very good, Madhav. 1 and pi by 2, excellent, excellent, excellent. Fourth one, 3 and minus pi by 2, very good, very good. Fifth one, yeah, fifth one, modulus is 0 and argument is not defined. Argument is undefined. Okay, for a 0 complex number, the argument is undefined. Don't say 0, it is undefined. It can be anything actually. It is the same way as asking somebody what is the degree of 0 polynomial. It could be anything. Or what is the direction of a 0 vector or a null vector. It could be anything. Okay, so right, No. You can't say shortest angle is 0. It is undefined. It can be any angle. It can be any angle. A point doesn't have an angle, right? Next, sixth one. Sixth one. You are trying to formalize it with a formula, Gayatri. Okay. So there is a formula, but it is not as simple as doing tan inverse of y by x. That always doesn't work. We'll come to that formalization in some time. Yeah. Root of 40. Are you sure? Isn't it root of 8 only? Ah. Yeah. And minus pi by 3. Absolutely. Absolutely. It is going to be minus pi by 3. Okay. Very good, Aditya. Last one. Yes, last one. Modulus is root 2. And argument is, I think we did this. Argument is, okay, now Shreyas is asking me how do we find out the argument very briefly. So Shreyas, I would like to take the last question as an example. So principal argument is defined as the shortest angle which you can make from the real z axis to the line connecting the complex number represented like a point on the argand plane. So this is the angle that you have to cite. And if this angle is measured in a clockwise sense, it would be a negative angle. And if it is measured in an anti-clockwise sense, it would be a positive angle. Correct? So in this case, your angle is measured in a clockwise sense and it has a magnitude of 135 degrees. So this will be minus 3 pi by 4. Okay, minus 3 pi by 4. Understood, Shreyas? Especially Shreyas, I explained here because I think the network was not that great. Did you get it? Okay. Now, just to answer Gayatri's question, normally a formula is told in the school. Okay. So what is that formula? I just quickly discuss with you. The formula is, if your complex number happens to lie in the first quadrant, there is a direct formula to get the argument. So if your complex number happens to lie in the first quadrant, your argument can be found out by using tan inverse of b by a. Okay, tan inverse of b by a. Okay, many books will say mod b by mod a. It's fine because a and b anyways are in the first quadrant, so they are positive. Okay, if it is in the fourth quadrant, it is negative of tan inverse mod b by mod a. Okay, so you can all find tan inverse of mod b by mod a. It would be an angle in the first quadrant only. Attach a negative sign, that will give you your answer. If your complex number is lying in the fourth quadrant. Okay, if your complex number lies in the third quadrant, your argument is defined as pi minus tan inverse mod b by mod a. Okay, and if your complex number lies in the third quadrant, your answer is minus pi plus tan inverse mod b by mod a. But this formula I strongly discourage you to remember, because you are already bombarded with so many formulas, right? Maths is not about knowing these formulas. So they are just a formulation of whatever concept we learned. Now, in order to complete this schematic diagram, if it lies on the real z-axis, it is 0, which anyways will be covered by this. Okay. If it lies on the negative z-axis or negative real z-axis, it will be pi. If it lies on the positive imaginary z-axis, it will be pi by 2. Basically, I'm taking care of the quadrantal positions. And if it is lying in the negative imaginary z-axis, it will be minus pi by 2. So if you remember this schematic diagram, if at all you remember it, okay, you'll be able to answer all your questions quickly. Same thing as we did it in trig. Yes, Harihara, correct. How do you know it's 135 degrees? Akash, to answer that, I have to teach you basic trigonometry. If this is 1 and this is 1, if this length is 1, if this length is 1, isn't this 45 degrees? So isn't this 135 degree in magnitude? So 135 is 3 pi by 4. Okay, simple trigonometry. Don't forget your basic trigonometries. Now, once this is clear, it opens our way to understand the second representation, which is what we call as the polar form. Polar form representation. It is also sometimes called as the vector form. It is also sometimes called the trigonometric form. Trigonometric form. All of them basically mean the same. It's just that different terms are being used for it. Now, please understand here. The concept of polar form representation has come from the concept of writing a point in the Cartesian form in terms of the polar form. Okay. So if we write a point A comma B in terms of r and theta, how will you write it? So we'll say, sir, simple. A is nothing but this length. Okay. B is nothing but this length. So as per our relationship between A, R and theta, A will be R cos theta, B will be R sin theta, correct? So the very same complex number which you used to write it as A plus IB, now it can be written as R cos theta plus I R sin theta. In other words, it can be written as R cos theta plus I sin theta, correct? Okay. In other words, you can write it as modulus cos arg z plus I sin arg z. And therefore, modulus and argument concepts were taught to you before I introduced the polar form. Now, it makes one feel, why at all we need this, right? I'm so happy with the point form. Why do I need to write it in polar form? I understand your concern at this point of time, but wait, when we start doing multiplication, division, etc., you would realize that polar form makes more sense to us vis-a-vis point form. For polar form will be giving us more insights as to what operation is happening when you're multiplying or dividing complex numbers vis-a-vis the point form, right? So even if the expression looks complicated prima facie, later on you realize that it is worth learning it because it makes your life simpler when you do operations like multiplication, division, or to a certain extent square rooting, etc. of the complex numbers. Okay, so it has its own advantage, right? So see, it's like somebody asking me, I'm happy with 1. Why do I need to write it like this? Or why do I need to write it like this, right? Well, each form has its own way, own importance, right? It's not like, this form has a drawback or this form has a drawback and this form has an advantage. It's just the representation of the same, number 1, but we use it in different situations. Okay. So when you write a complex number like this is what we call as the polar form of a complex number. Many a times we write this in a short form as R cis theta. Okay, cis is you can say a short form of cos theta plus I sin theta. Okay, but not to be used in school. Please, sincere request, No cis bro business in school. Okay, don't do cis and bro in school. They will simply cut marks. Okay, this is something which is for our internal understanding because we don't want to write too much. So why do we choose this abbreviation? Because we don't want to waste writing the cos of the angle theta and sine of the angle theta, because ultimately theta is same in both the places. So why not write it one single time? Okay, it is, if it is deleted in school, very good. Thank you, stars, for it. But I don't think so it will be deleted for JEE. So this is the acronym. And in JEE, whatever you use, they don't care about what intermediate step you use. They are only bothered about the final result, whatever you bubble up or whatever you choose as your options. Okay, is this fine? Okay, so now I'll just give you some questions to write some complex numbers in polar form. It doesn't need a separate discussion because you have already known how to find modulus and argument. So we can directly jump with the question. I think I have seen some questions before. Yeah, there you go. Just ignore exponential form as of now. Ignore Madi. I'll talk about it in some time. So let's write down the following complex numbers in the polar form. First one. Just mention in your answer, for example, in this case, I'm going to do it for you. In this case, your answer will be 2 root 2 cos 3 pi by 4 plus I sine 3 pi by 4. Okay. I would request you to save your time and write it as cis 3 pi by 4 like this. I'll be more than happy. Okay, Akash wants me to go back to the top of the slide. Top of this slide, this is already the top. Oh, top here. Okay. Akash, done. Okay. So first one I've already done, so no need to do it. So 2 root 2 cis 3 pi by 4. I want you to try second, third, and fourth. Done. Second one. Okay. Second one, the answer that you should get is 2 cis. This will give you minus, yeah, this complex number is located over here, correct? Minus 1 minus root 3. Okay. So this is 1 and this is root 3. So this is 60 degree, but you have to count it from this direction. Okay. So it's minus 2 pi by 3. Okay. Third one. Yes. Now, with respect to this, guys, first we have to simplify this. In the denominator, you will have 4 plus I square minus 4i. That will give you 1 plus 7i by, and this will give you 3 minus 4i. Correct? Most of you are waiting for me to solve this. So we'll take this up. And now, the first thing that we need to do is, we need to make the denominator real. And how do we do that? Later on, you will learn that we multiply it with its conjugate. This is called the conjugate of this particular complex number. In fact, both are conjugates of each other. We will talk more about conjugates in some time. Don't worry about it. I'll be speaking about conjugate in detail. We'll be doing many properties related to it. So this will become 3 square plus 4 square, which is actually 25. Numerator, This actually gives me an opportunity to discuss multiplication also of complex numbers, even though I wanted to take it separately. So 1 into 3, this into this will give you 3 minus 28. Okay. And then we'll have 1 into 4i, and this into this will give me 25i. So this actually gives me minus 25 plus 25i by 25. If you see, this complex number is just minus 1 plus I. Minus 1 plus 5 is a complex number located in the second quadrant. Am I right? And the distance of this from the origin is root 2. And this angle is going to be 3 pi by 4. So the third complex number, which was written to you in a very, you can say, ugly fashion, this was actually root 2 cis 3 pi by 4. Anybody who got that? Again, don't worry if you have not got it now, because it involved several operations which you have not done so far, like multiplication and multiplying with the conjugate. So third one was okay. If you have not got it, no problem. Let me check if somebody has got it. Oh, Anurag got it. Nice. Very good. All right. For the fourth one, let's figure it out. In fourth one, many people would wrongly believe that the argument is theta. Please let me tell you, it is not. This is not a polar form representation. Okay, right? In fact, we have to convert it to a polar form representation. It is just a point form representation. So you may treat this as your A, this is your A, and this is your B. This is your B. So when you write it, okay, first of all, you have to figure out what is the modulus. Modulus would be under root of 1 minus cos theta whole square sine theta whole square. I'll tell you another way also to do it, and that will be a much faster way. Okay. So when you do this, it becomes under root of 1 plus cos square theta minus 2 cos theta plus sine square theta. Cos square plus sine square will become a 1. So it will be 2 minus 2 cos theta. Okay. And this will become under root of 4 sine square theta by 2. Now don't ask me how. It is because cos theta is 1 minus 2 sine square theta by 2. Remember your half angles formula. I'm using that over here. Okay. Now they have mentioned theta is between 0 to pi because they wanted you to know that this answer will just become 2 sine theta by 2. Because ultimately this answer should give you mod 2 sine theta by 2, right? Guys, this is something which we have done in the bridge course also. Under root of square of something gives you mod, right? Don't forget that. And since your theta is in the interval 0 to pi, this fellow will be positive. If this fellow is positive, mod becomes redundant. So you'll just have 2 sine theta by 2. Is that fine? All right. Now, what about the argument? Now, if you see, 1 minus cos theta is a positive quantity. This will be a positive quantity because your theta lies between 0 to pi. This is anyways a positive quantity because theta lies between 0 to pi. So in which quadrant this complex number will belong? You'll say, sir, both A and B are positive, so it should fall in the first quadrant. In the first quadrant, as for the formula that we have seen, argument is tan inverse of B by A or mod B by mod A. Doesn't make a difference because they're positive. So if you do tan inverse of B by A, B will be sine theta, A will be 1 minus cos theta. Correct? Let us use our half angle formula. So this will be tan inverse. This will be 2 sine theta by 2 cos theta by 2. Okay. And this will be 2 sine square theta by 2. 2 gone. Sine theta by 2. Sine theta by 2 is gone. And this would leave you with, tan inverse of cot theta by 2. Tan inverse of cot theta by 2 is pi by 2 minus theta by 2. right? So if you write this in the polar form, your answer will be 2 sine theta by 2 cis pi by 2 minus theta by 2. This will be your polar form. Is it clear? Is this clear? Now, there's an alternative way also to do it. So instead of doing all these things, you can directly use your half angle formula straight away. Something like this. Correct? Take 2 sine theta by 2 common. Okay. You'll end up getting sine theta by 2 plus I cos theta by 2. Am I right? But in your polar form, there should be cos here and sine over here. So what I will do is, not much of an issue. I will write sine theta by 2 as cos pi by 2 minus theta by 2 and cos theta by 2 as sine pi by 2 minus theta by 2. Make sense? We end up getting the same result. 2 sine theta by 2 cis pi by 2 minus theta by 2. What is the path it would trace? As in, if your theta varied, okay, if your theta varies, the path that it will trace would be obtained when you eliminate theta from both of them. So yeah, that could be one of the questions. So if your complex number is, this is just to answer Mr. Madhav. So let's say if you had this as a complex number, then x is 1 minus cos theta and y is sine theta. So your cos theta would be 1 minus x. Your sine theta would anyways be y. Use the formula that cos square theta plus sine square theta is equal to 1. So this is the path that it will trace, and it is that of a circle, my dear. Because it is, sorry. Yeah, because it is that of a circle whose center is at 1, 0 and radius is 1. Okay, so this is a circle. Anyways, we'll come to it a little later on in this chapter. Anyways, we have those locus based questions coming up. Okay, we'll discuss about it in detail. Later on, we'll talk about it. So as of now, no problem in understanding the polar form representation. No questions? Okay. Moving on to another form, which is what we call as the exponential form or the Euler's form. Exponential form or the Euler's form. Okay. Euler, remember the Swiss mathematician Leonhard Euler. Okay. One of the biggest mathematician of his times, and I think of all times. The guy who went partially blind, right, and still published so many papers in the field of calculus and number theory. Okay, so this guy Euler, he was very instrumental in developing several theories in differential calculus, or for that matter, differential equation. Okay, so what he figured out that this complex number that you are actually writing as r cos theta plus I sin theta, he figured out that you can also write it as r e to the power I theta, right? That is, he figured out that somehow, I'll tell you how he figured out that this could be written as e to the power I theta. Okay. Now there are two ways to figure it out. One, which is actually what Euler used, and the second is your Taylor's expansion or your Maclaurin-Taylor's expansion. But Maclaurin-Taylor expansion came much later. It probably came after the death of Euler. Euler was not even aware of there is an expansion like that. So he probably did not use expansion to prove it. He probably used differential equations to prove it. How? Let's check. So what Euler did, he said, okay, let's call this cos theta plus I sin theta as a variable x. Okay. And given that he was working with calculus a lot, he differentiated it with respect to theta. So cos theta derivative is minus sin theta. I being a constant, that remains I. Sin theta derivative is cos theta. Okay. Now what this guy did, he wrote this minus 1 as I square. Okay, and he took I common. So if he took I common, he got cos theta plus I sin theta. So he realized that on taking I common, he is back to I times the same number that he started with. Okay, so he ended up getting a differential equation. This is what we will learn later on in our class 12th. This is actually a differential equation. Okay, this is the first order, first degree differential equation. Differential equation is a subject matter of class 12, so we'll not go much into details of that. But we'll learn how to solve it very briefly over here. So what he did was he then did something which we call as variable separable method. So he separated x along with dx and he brought the d theta up. Then he integrated both sides. And then he realized 1 by x derivative with respect to x is ln x, and I d theta is I theta plus a constant of integration. Remember, whenever you are performing any indefinite integral, you should always write a constant of integration to summarize it. Always write a plus c to summarize it. Okay. Now, in order to find this c, what he did was he said that your x value when your theta is 0 is actually a 1. So what he did was he put theta as 0 here, and he realized that when he put theta as 0, x becomes 1. So he knew a particular value of x when theta was 0. So here also, when you put theta as 0 and x as 1, this condition must be satisfied. So later he realized, in fact, here he realized that his c value comes out to be 0. In other words, this expression is as good as ln x equal to I theta. And then he took NT log on both the sides, and he figured out that, oh, that x, which was cos theta plus I sin theta, can also be written as e to the power I theta. Okay, and he started using, instead of cis theta, e to the power I theta, and hence the Euler form representation of the complex number. It is one of the most, you can say, powerful form of representation of complex numbers, because it allows you to do multiplication, division, log, nth power of a complex number very, very easily. With much ease and comfort, you can do that. Okay, is this fine? Okay, later on, when Taylor expansion was basically, Taylor started using expansions. So what he did was he wrote cos theta as, we all know our Taylor expansion, Maclaurin's Taylor expansion. So it can be written as 1 minus theta square by 2 factorial plus theta to the power 4 by 4 factorial minus theta to the power 6 by 6 factorial, and so on, correct? And sine theta, you can actually write it as theta minus theta cube by 3 factorial plus theta 5 by 5 factorial minus theta 7 by 7 factorial, and so on till infinity. Okay. So if you see his terms, it is actually 1 plus I theta. So 1 plus I theta. Next term is minus theta square, which he actually said can be written like this also. Correct. Next term is minus I theta cube by 3, which is actually plus I theta cube by 3 factorial, and so on. So later he realized that, Taylor and Maclaurin realized that this is actually the expansion of e to the power I theta. Okay, I hope you all remember in e to the power x, the expansion goes like this. Those who were there with us in bridge course, this is what we had learned in our limits chapter. So if you replace your x with I theta, this is what you will end up seeing. Okay, so there are multiple ways. Now remember, in the beginning of the chapter I told keep theta in radians, is because these expansions that you have written, they are applicable when your theta is in radians. So this expression is to be written when your theta is kept in radians, else it will become a divergent series. Okay, so this is just an extra information. You will not find these derivation in books, so please make a note of this. I will come back to this form. I have a lot of things to discuss about this form. As of now, I will stop with respect to the representation of complex numbers over here.